So to this point, we have seen that work is the process of moving energy from one system to another. Or sometimes we look at it just in the context of energy leaving some system or coming into some system without worrying about where it goes. Of course, it goes somewhere. But work is this process, and we've seen by the work energy theorem that this is, we've seen the definition of work. Let me start there. Integral from A to B of F dot dr. And then by the work energy theorem, this is equal to the change in kinetic energy. So what we have here are what are called mechanical processes. These, undergoing a displacement is a process. Changing your kinetic energy, which in this case means changing your speed, is a process. And all mechanical processes, at least in this universe, take time. So it makes sense to be able to talk about these processes in terms of the time it takes them to complete. Of course, that, it could be different for any different number of systems. You could slow down your car really quickly if somebody in front of you starts to slam on their brakes, or you could slow down really slowly if you see a stoplight a couple hundred yards ahead. Those processes take time. In both cases, you stop and your change in kinetic energy is the same, but one of them involves a lot more time than the other one. So if we want to know something about the time it takes a process, the standard procedure is to take some sort of delta work over delta T. Sometimes you'll see this written as energy expended per unit time, right? Work has to involve an energy moving around. We're going to stick with just this delta W over delta T. Of course, in the limit, as delta T approaches 0, this can become dW dt. This would be something like the average, and this would be the instantaneous. Instantaneous what? Well, what we're talking about is power. Your book is going to use a script P for this. I'm not going to try it. We're just going to use a P. P is defined as this dW over dt. Of course, there are situations which you can use the delta. If you have smooth changes or discrete changes, you can use the delta, or you can integrate, you can take a derivative. Either way, in physics speak, this would be the instantaneous power, this would be the average power. What I'm saying is there's some situations in which the average power is the same as the instantaneous, just like we saw with things like velocities. But we'll stick with this. The power is defined as the change in work per unit time, dW dt. Units of this, units of work are joules. Units of time, of course, are seconds. And we're going to wrap that up and name it after James Watt. So this is a W, which stands for watt. It's a little unfortunate because W is the symbol for work, which has units of joules, but W is the unit of power, which stands for watt. So you got to be it's going to be clear from context, but you have to be careful how you handle your W's here. Now, the unit of a watt is familiar to anybody that's ever changed a light bulb, right? 100-watt light bulbs, 50-watt light bulbs. This is what it's measuring. It's measuring energy expenditure per unit time. How much energy is that bulb putting out per second? If you've ever paid an electric bill, you might have you might have seen on your bill, kilowatt hour. This is not really something we deal with in this class. But kilowatt, we know what kilowatt is. It's 1,000 watts. And then you have this unit of time. So let me just forget about the actual hour and say this is a unit of power times time, right? Well, if power is work per unit time, if I multiply power times time, I get back work, or in this case, I'm going to get back energy. So you're literally paying the electrical company for the energy. They just give it to you in these kind of strange units. Kilowatt hour is a unit of energy. It's kind of weird. You can get a joule out of it if you run the conversions, but that's what that is. It's a unit of energy. It comes out of this idea of power. So, what can we do with this? I should say that's really it. that's power in a nutshell. But there is one thing that's a little bit interesting here. If I remember, that work is defined as as a force times the integral of a force times the displacement, right? Well, I can say this: power is equal to d dt of integral from a to b of f dot dr, right? Well, the derivative of an integral is just the integrand. So what I can do here is form f dot dr dt. Let me rearrange this to read f dot dr dt. dr dt, this is a generalized displacement, but der being a displacement, the time derivative of that is just a velocity, right? So I can rewrite this finally as f dot v, and we have now an explicit relationship between forces and velocities. I should point out that in this class, this is the last you'll ever see this. I'm never going to use this, but your book does mention it, and I think it's important to see. Number one, to know that you can do different things with these quantities we're talking about, past what we just explicitly talk about in class. And number two, to see that there are explicit relationships between things like forces and velocities, which we don't normally think of because we think of accelerations explicitly related to forces. But there are other ways to formulate it. But as far as what I'm concerned for the class, from here up is what you need to know. I wouldn't worry so much about the last one, but it's useful to look at.